I'm Thor Moody with Delorier. We're here today to talk a little bit about in preparation for concrete test specimens so that they can be tested in compression in the laboratory to confirm that they meet the specification for strength. There are several ways to prepare the end of a test specimen. The 4x8 is a little lighter, so I'll work with this one. But this end has to be perfectly smooth, as does this end, so that when it goes in the machine and it's put into compression, you got a very smooth surface that evenly distributes the load over the entire surface area of each end. Now there are several ways to do this. One is to use what's called capping compound, and it's generally a blend of sulfur and fly ash. It's melted at about 185 degrees. It stinks. It smells up the entire lab. Nobody likes using it, and it creates burn hazards. And the way it's done is that molten mixture is ladled into a mold that the cylinder is then lowered into, and it's allowed to cool and harden. It's removed, flipped over. You do the same thing to the other end. Sulfur capping is kind of a thing of the past when it comes to testing cylinders because there's a better way, and that's using compression pads. These were originally developed by Ashto, which is DOT guys. They were using bridge bearing pads, and they looked at them and said, I wonder if we can break cylinders with these. And they came up with a test method using neoprene pads to cap cylinders. They no longer have that test method in Ashto. They turned it over to ASTM, and now it's ASTM C1231, which is the unbonded capping system for test cylinders. A third way to prepare a test cylinder for testing is to grind the ends smooth with a commercial grinder. It's expensive, it's time consuming. It has to be ground to within like 0.02 of an inch, but it can be done. And some labs, some production facilities will use grinding machines to prepare their cylinders. For our purposes, we're going to talk about the unbonded capping system, the neoprene pads. Each of these pads goes into what's called a steel retainer. And this retainer keeps the pad from spreading laterally when it goes into compression, so that the pad will fill all the little voids in the end of the cylinder before the cylinder actually fails. These are for testing 4x8 cylinders. This is a 4-inch diameter retaining ring. Our compression pads are a little different than everyone else's. They're molded, not die cut. When you die cut, which is basically pressing a biscuit cutter into a neoprene sheet, you get a little convexity all the way around the perimeter. This is a molded pad where the material is actually injected into a mold. You get much better geometry on the pads, and the sides are nice and clean. But we also put these little nubs, which you may or may not be able to see in the video, around the perimeter, and that gives a little bit of space between the retaining ring and the pad so that you can get the pads in and out of the rings. Once you've got your pads and everything set up and you're ready to do a compression test, one retaining ring and pad will go on one end of the cylinder. The other one will go on the other end of the cylinder. Then this whole thing goes in the compression pad, or I'm sorry, in the compression machine. Once it's in the machine, you apply about 10% of the anticipated load, and then you stop it. And this has to be checked to make sure it's perpendicular. So we make a perpendicularity verification device. We call it a PVD, and it's a straight edge that goes right up against the side of the sample so that you can check it to make sure it's perfectly straight up and down. Now this is a PVD for reaching around a spacer that's in the compression machine. A lot of times, because they're set up for doing 6x12s, you have to put a spacer in there to reduce the stroke. And you have to reach around that spacer because the bottom of this has to be on your lower platen. So if there was a spacer in the machine, this whole thing would be higher, be up about here. So we would have to reach around it to get on the side. Now this one doesn't have that. So this is a PVD4NS, which means no spacer. That goes on your lower platen. You put it up against the side of the cylinder like that. And then we have a gap tool, which is sized for this length. And as you can see, as long as that gap tool will not pass between the PVD device and the specimen, you're good to go. If it does pass through, like so, then it's not perpendicular. You have to release the load, recenter everything, reapply the load, check it again. If you do it 2 or 3 times and you can't get it perpendicular, you're probably going to have to give up and either grind the ends or sulfur cap it. Chances are you've got something on one end of that cylinder that's far enough out of spec that it's going to have to be ground. So anyway, that's how it's done. We have pads in 6-inch, 4-inch, 3-inch, and 2-inch, and we have PVD devices for every size. 6-inch cylinders handled the same way for the 6x12. Retaining ring and pad on the bottom, retaining ring and pad on the top, perpendicularity verification device on the side, and it's perfect. One thing about the verification devices that everyone should be aware of, ASTM C39, which is the test method for compression testing a specimen, says that a 1/2 degree, which is the maximum out of perpendicularity you can have, is approximately 1/8 of an inch and 12 inches. People see that and they just go and they get an 1/8 of an inch drill bit or something that they know is 1/8 of an inch thick and they start using that. The reality is, this is not 12 inches. This is not 12 inches. So when we size our gap tools, they are sized for the distance we're checking, not 1/8 of an inch. You may see a change in ASTM about that, some change in that language, so it's not as confusing. So that's the unbonded capping system and the perpendicularity verification devices. If you have any questions on any of this, call our office and we'll try to answer them for you.